The force of gravity is a force between two masses. It varies with the product of the masses, g, and inversely with the square of the distance between them. This is the equation, where g is the universal gravitational constant, m1 and m2 are point masses, and r is the distance between them. Gravitational force is always negative because it is always attractive. Electrostatic force acts on two charges. The equation is similar, where it varies with the product of the charges, q1 and q2, Coulomb's constant, and inversely with the square of the distance between them. However, this force can be negative or positive because the charges can either attract or repel, respectively, depending on whether they are similar or opposite. Charge is carried by protons and electrons. The magnitude of this charge is called the elementary electric charge, and the magnitudes of all point charges are multiple of this number. But how do we know this number, the charge of the electron and proton? Two final equations are important to understanding Millikan's experiment. The electric potential is the potential electric energy per unit charge. This is the integral of the electrostatic force. Using rules of integration, we get this formula, where Q is the charge that is causing the field. Lastly, given two charged plates, we have a relationship between the electric field strength, potential difference between them, and distance. We get this by dividing the equation energy transferred equals force times distance by charge.
Here is a cross-section of the apparatus used in the experiment. The experiment was done in a vacuum to avoid collisions between the oil droplets and the air particles that could have an effect on the final result. The chamber has two slots on the right, the atomizer and the microscope. The atomizer, similarly to a perfume spray, sprays out tiny oil droplets into the chamber. As the droplets move, they lose electrons and gain a positive charge. Now, before we look through the microscope, we must realize that these two plates within the chamber are charged using a voltage. Looking through the microscope, we can see that the positively charged droplet has a gravity force acting on it, pulling it down. Also, there are two forces acting on it as well, the attraction and repulsion force from the plates. The sum of those two forces will give us our electric force acting upwards on the droplet. The magnitude of the electric force will depend upon the voltage supplied. When a high voltage is supplied, the electric force has a larger magnitude than the gravity force, therefore the droplet moves up. The same happens in the opposite way when a low voltage is supplied. However, when the voltage is just right, the droplet will float. This means that both the electric force and the gravity force are equal. With this in mind, we can form a data table of when the droplet floats with its mass and voltage recorded. This is done of droplets with different sizes. Now, going back, we know that the droplet floats when the force of gravity equals the force of electricity. The force of gravity is dependent upon the mass of the droplet, as g in the equation W equals mg in this case remains constant, therefore m is the only variable. The force of electricity is dependent upon the charge of the droplet and the voltage supplied to the plates. We can now see the different variables in the equation, and we've obtained two of them experimentally, the mass and the voltage, so we can now rearrange the equation to solve for the charge of the droplet. The results obtained looked as such. Remember that they are positive, as the droplets lost electrons. But something that they noticed is that the charge of the droplet is always a multiple of 160, which means the droplets were losing charge in multiples of 160 each time. So we can now conclude that the charge of an electron is 160 zeptocoulombs, which is equivalent to 1.60 times 10 to the power minus 19 coulombs.